everyone, and welcome to today's STERIS Tech Talk on establishing specification limits for ethylene oxide sterilization. STERIS Tech Talks are a series of webinars covering subjects relating to gas and radiation sterilization processing and the laboratory testing and validation services which support these processes. My name is Ashley Maru, and I'm the Associate Product Manager for STERIS Applied Sterilization Technologies. I'll be the host for today's event. Our presenter today is Carrie Clark. Carrie is the Senior Director of Gas Technology and Laboratories for the Americas region at STERIS AST. Carrie joined STERIS in 2017 as the Manager of EO Process Technology and has subsequently held positions of increasing responsibilities encompassing the ethylene oxide sterilization facilities in North and Central America and the Brooklyn Park, Minnesota STERIS Laboratory. Carrie has accumulated over 25 years of experience in industrial sterilization, strategic supply chain analysis, biocompatibility, controlled manufacturing environment design and construction, and microbiological laboratory management while working in the medical device manufacturing industry. Carrie is an active member in ASTM and AMI working groups, and is recognized as an industry leader and subject matter expert in the field of EO sterilization. All attendees are on mute for the presentation. However, we would like to encourage everyone to submit questions using the questions function on the GoToWebinar control panel. Questions will be answered following the presentation. Today's presentation will be recorded and uploaded to our STERIS Applied Sterilization Technologies YouTube channel. Please note that continuing education credits are not provided as part of this webinar. And now over to Carrie to begin the presentation.
Greetings to everyone, and I appreciate you attending today. You can see our agenda for this presentation. We're going to be talking about understanding the measuring systems that are used in EO sterilization technology. We'll have a discussion about precision and accuracy that should be the theme throughout the talk. We'll talk about data rounding and appropriate mathematical principles for rounding, parameters and units of measure that are used for the different parameters, application of tolerances for the parameters, setting your upper and lower limits, modes of failure that need to be considered and the best way to analyze them, critical parameters for your processes, and then a short summary and recap. So starting off our talk, we're talking about understanding the measuring system used in EO sterilization. You've got all sorts of equipment that measure all sorts of attributes of the cycle, including the clocks that give the timestamp for the various steps in the process, thermocouples that measure temperature within the chamber, pressure transducers that help to control when the machine steps into the next step or phase. Weight scales, you need to know how much EO is being put into your process, and then installed or remote sensors for EO concentration and relative humidity if you're going to be doing parametric release. So when we set out to measure a parameter, we want to consider the accuracy and the precision of the measuring system. We don't want to paint ourselves into a corner by making things far too accurate or too precise. So let's talk about those two elements right now and what they actually mean. So accuracy is defined as the closeness of a measure to a true value. In other words, if you have your target or your set point, how close can you come to that set point? How far is your spread from that set point? And the precision is the amount of resolution in the measurement. So precision is how closely clustered around the center point your data are. So if you were to measure the same parameter a multiple number of times and you find that they're very closely clustered, then that's good precision. But if they're way away from the target, then it's not very good accuracy. And here's a really good illustration of that. If we look at the lower left corner, you'll see that we were doing target practice on the archery range, and we hit the target all over the target. We even missed it one time. Well, that's not very accurate, nor is it precise. If we move to the lower right-hand corner, you'll see that the arrows were closely clustered. So they were very precise, but they were quite a ways from the center of the target. Therefore, there wasn't very good accuracy. Now moving up to the upper left, you'll see that we had pretty good accuracy because they were, you know, it's a nice good pattern. It's centralized around the center point of the target, but it wasn't precise because they weren't closely clustered. And then the upper right, you'll see that there was a close cluster. Everything was around the center point, so it's both accurate and precise. So when we start looking at the elements of parameters, we want to make sure that we are not giving ourselves a false sense of accuracy simply by adding precision. You can have very good precision but not be accurate. We'll explain that a little as we go. So first, let's talk about the different parameters and what type of precision is needed for those parameters. You'll see that for timestamps, your clocks, it needs to be precise by the hour and the minute, but not out to the second, because that's requiring too much precision for the measurement in the process. Because sterilization processes take place over hours of time, the seconds really don't matter. So you don't want to set your parameters in a way that being 2 seconds over or 4 seconds under is going to cause you to have a discrepancy. Pressure, it depends on the type of unit you're measuring with. If you're doing inches of mercury, then 1 decimal place is sufficient. If you're using millibar, you want whole units. Pascals, 1 decimal place, and PSI, 1 decimal place. We'll talk about the instrumentation, the pressure transducers in just a moment as an example to understand how all that comes into play with 1 decimal place versus whole units. For temperature, again, whether you're doing Fahrenheit or Celsius, you want whole units. 1/10 of a degree really doesn't make much difference if you have a plus or minus 10-degree spread in your processing parameters for your upper and lower limits. So don't paint yourself into a corner that is really unnecessary. Relative humidity should also be recorded in whole units and not in fractions. No 0.1 decimal place is not a good idea. Absolute humidity is also recommended to be in whole units, because a milligram per liter is 1 milligram of water. That's a pretty small increment of measure already, so you don't need it to be more precise than that. EO concentration, again, in milligrams per liter, you want it to be in whole units. And even a lot of times whole units gives you a false sense of precision, because a lot of the SEC sensors and IR sensors are only good at plus or minus 30 milligrams per liter. So consider that when you're doing this. For your weight scales, it also needs to be in whole units. 1/4 of a pound or 1/10 of a pound isn't going to make much difference when you're using large quantities of EO. If you have a 1 pallet chamber, then you're still going to look at, oh, we used 1 or 2 pounds of EO in this little tiny chamber, but most chambers are rather large, so whole units is sufficient. Talking about mathematical rules for rounding, I gave the example of PSI a couple of moments ago. Pressure transducers are considered to be, they're normally calibrated for accuracy at plus or minus 0.02 PSI, using PSI as the example. So according to mathematical rules of rounding, if you're going to be reporting to the 10th place, the 0.1 place, then you would have to have accuracy out to the 0.001's place, or 0.005. Your margin of error falls 1 decimal place beyond what is reported. So for pressure transducers, because their accuracy is at 0.02, usually plus or minus 0.02, then the accuracy is going to fall to the 10th place, because the 100th place is the one that determines the accuracy. So for a reading of 7.23, it would need to be reported as 7.2. And a lot of people say, oh, well, it's good to the 100th place. Okay, Well, if it's at the hundredths place, then 7.23 could be 7.25 or 7.21. So does that really matter in the long run in the big picture of things? We'll see that this used in just a few slides, where we will actually talk about pressure changes for relative humidity and pressure changes for EO concentration to understand better how the rounding impacts us. So in this situation, the digits in the second decimal place would be rounded according to convention. If they're 0 to 4, then they round down, and if they're 5 or greater, then they round up. Now here's an example of temperature. So we see if the specification is 50 Celsius with a tolerance of plus or minus 5, so your upper and lower tolerances. If you put a false sense of accuracy and precision into the lower control limit and upper control limit, you'll see that one company established an upper limit of 55.4, a lower of 44.5, and in reality, it's not going to make a difference. Another company said, oh, our specification is 50.0 with a plus or minus 5. So they had their lower control limit at 44.95 and their upper control limit at 55.04. Again, adding extra decimal places is not going to help us. So then another company said, oh, it's 50.0 plus or minus 5. So we're going to say 45 to 55. In reality, just drop the decimals. It's okay. If you round up 1 degree or down 1 degree, it's not going to make that much difference, especially if your tolerance is a span of 10. Back to the PSI example. Here's an example where steam is injected, and sorry, I'm bouncing back and forth between metric and English. So steam injection at 130 Fahrenheit, if the pressure transducer can record up to 0.74 psi, and again, the 4 is a false sense of accuracy, but we do the calculated values for relative humidity, a change in pressure of 0.74 psi gives you 33% relative humidity. If you round it down, because the 4 rounds down, and you round it down to a 1/10 decimal place of 0.7, the resultant value is 31% RH. So by rounding down, it looks like you lose 2% RH. Now let's go the other way. If you round it up, let's say the delta was 0.85, the calculated relative humidity value is 38%. If you round it up, then it rounds up to 40%, again, a difference of 2% RH. Now let's consider the fact that even though the pressure transducer has a very good accuracy at, plus or minus 0.02, and we could say, oh, let's make sure that we capture that number. In reality, when you're physically measuring inside the chamber, the SEC sensor or the IR sensor, however you're measuring your humidity in the chamber, is good for plus or minus 5%. So you'll see that rounding up or rounding down still falls within the accuracy of the sensor itself. So using the resultant value of 40 that's over on the right, it could be as low as 35% RH or as high as 45% RH based on how your sensor is functioning. So by adding that extra decimal in the hundredths place for PSI, you're creating a false sense of accuracy, and you don't need to do that when setting your limits. So keep it in the at the 0.1 level for PSI, and then the chart earlier gave recommendations for other units of measure such as inches of mercury, millibar, etc. The same goes for using pressure for EO concentration. That's another important aspect of our sterilization process. So let's look at how rounding affects EO concentration. If we have a delta of 4.33 psi, the calculated value is 4.82. If we round it down, it's 4.79. a difference of 3 milligrams per liter. That's less than 10% difference, and that's, if I did my math right, and that's exactly, it's very, very minimal impact on your cycle. You're going to get just as much lethality at 479 as you are at 482. Then let's say we take a different delta, 4.35, and we round it down to 4.0. We have a difference of, again, 5 milligrams per liter. And given that the sensor accuracy for EO concentration on an SEC sensor is plus or minus 30, you're still well within the accuracy of the device by rounding up or rounding down. It's not going to impact the outcome of your process. When we talk about time increments, time is exceptionally important in the sterilization process because there's a lot of time and effort that goes into understanding how long the cycle needs to be, how much chamber time it takes, what the turn time is or the cycle time for your product in general. You want to get your product into and out of the process as quickly as possible. You don't want to eat up machine capacity by making the process too long. You have to balance that against how short the cycle can run to actually have the lethality you need, the sterility assurance level that you need, and the EO residual content that has to be proven because of the exposure to EO. So measurement is usually in terms of hours and minutes, and that's fine. Don't make it seconds because that's much too precise and you can get yourself into some non-conformance situations if you try to make it too precise. So time, usually the maximum amount of time that you set for your cycle can be based on the heat history that you used when you were, when the medical device manufacturer was establishing the shelf life, doing accelerated aging, etc. If you look at the amount of heat history that's delivered to the device that established your testing and whether or not your product functioned after all of its manufacturing processes, after sterilization and after aging, you may be able to say, hey, our product is able to take 130 Fahrenheit for up to 90 days accumulated heat history time. So if the time on my process goes over by 2 hours because something happened with the sterilizer and it wasn't able to step into the next process, and so my cycle ran long, 2 hours, 4 hours, 6 hours, you know, if there was a power outage and the machines actually just completely shut down and they couldn't get the product out of the chamber for an extra 6 hours, did it damage your product? How much time can you actually allow the process to run without the heat inside the chamber damaging the product? That's the main question. So you can look at the heat history that you have in the testing for the product to determine whether or not you need an upper limit at some point for the process. The minimum time, however, is a little more tricky because the amount of time during the dwell phases for humidity or conditioning and EO dwell will greatly impact the lethality of the process. So overextending the process probably doesn't impact lethality, it would impact function. Under-processing can impact lethality. So you want to make sure that your minimum time is based on data that you've collected from your sublethal cycles. You can look at the amount of time that would be required for spore log reduction to occur at the appropriate levels for the sterility assurance level that you want to achieve. And then you look at the sterility assurance level either through a calculated method or through your half cycle both of which are overkill approaches for sterilization. But then you should confirm the minimum time during your MPQ in your validation, your microbial performance qualification. For time, you want to make sure not to over process your product any more than necessary. So you do want to try to establish the minimum time and give yourself some cushion on the back end so that if the cycle runs short, you still have your lethality proven, but if it runs over, you have data to support that the product is not damaged. For time in EO dwell, you would also need to have EO residual data to show that your product is not going to retain EO any more than it would in a normal process if it's been over-processed during EO dwell. So another consideration you want to take is the amount of time between load removal from preconditioning and the commencement of the sterilization process. It should also be in hours and minutes. And during the validation, you're going to establish that time to show that the load will still continue to retain the temperature and humidity that it needs in order to process easily and within the boundaries of your validation. Your practices should be defined as to whether placing the load inside the chamber and then closing the door is considered initiation of the cycle, or if it actually means pushing the start button. You want to document what your practices are so that there's no question for regulatory authorities that come in. Temperature tends to be a reoccurring theme here. The ISO states that temperature and pressure throughout the cycle should have established parameters. In section, I think I have it referred to later, 10 point, sorry, I won't quote it. I'll wait till I get there. So temperature and pressure should have established parameters. You want to look at the different phases of your cycle. If you have all in one, then obviously all your temperature is going to be required at different phases when the product is in the chamber. If you have a three-step process, the preconditioning and aeration phases usually have a pretty big range of temperature that's used. So you want to try to test those areas in the coldest spots. Typically, you don't worry about the hottest spots because the coldest spot is the biggest challenge. So generating data at the coldest spot within the aeration room when you're testing residuals, and then in the coldest spot in the preconditioning room before you're going into lethality is the best way to look at generating data to support your upper and lower ends. Then during chamber processing, when you're putting gas, EO, nitrogen, air, whatever it is you're putting into your chamber, it's not unusual for temperature fluctuations to occur in quite wide swings because of Boyle's law and the way temperature and pressure interact with each other. So you want to make sure that you have a fairly wide temperature allowance for those phases, but then for your conditioning phase and your EO concentration dwell phase, your EO exposure phase, you have tighter parameters because those will definitely affect how it's interacting with the product, being absorbed into the product, ushering the EO throughout the chamber and distributing it, etc. So you want data on file for validations from validation studies that were used to establish the lower limits, and that can be costly if you're trying to run your validation at 125 C, but you're actually going to be processing at 135 C. It's a bit expensive to run those extra studies, but it would open up the lower end to generate data to prove that you can sterilize at those lower limits. Pressure and weight. So almost every sterilizer is going to utilize a change in pressure as the primary control for introducing EO into the chamber. And here's the reference I was alluding to a moment ago and I was stumbling over myself, sorry. The ISO requires that you have EO delivery measured, and pressure is the typical way to do it. It does state that if pressure is used as the primary means of control, then the requirement for a secondary measure is only to confirm that EO is admitted into the chamber. And what I've seen quite frequently is that a company will say, here's my upper and lower limit for pressure for EO injection. And then they'll say, oh, and I also have this the weight of the gas going into the chamber. We have to have X number of kilograms or pounds of EO weight change on the scales. And actually, you don't have to have an upper and lower parameter for weight. You need to have it recorded, but that's only to prove that EO did go into the chamber and it wasn't something else going into the chamber besides EO. So your pressure indicates EO is going in. Your drum weight change confirms that it truly was EO going into the chamber because your weight scale changed. But you don't have to have an upper and lower limit for weight. You can also use things like load cells or mass flow spectrometry. I'm using the wrong term, spectrometry. And those should be measured in whole units as well. So if you're using a mass flow meter, then you can measure the amount of mass that went in. But again, it doesn't have to be an upper and lower limit. You have to just show that mass of EO did go into the chamber, and using those types of measuring devices can prove that it truly was EO that caused the pressure change. Now, processes for parametric release. You do have a secondary measurement for EO concentration to be measured in the chamber. We will be having another seminar in a couple of weeks on actually June 23rd that talks about parametric release, and we'll have a lot more information on how to do that, what's to be done, etc. So I would greatly encourage you to tune in at that time. Again, June 23rd for parametric release. So the secondary measure of EO for parametric release must be measured by direct measurement of concentration in the chamber. There does need to be an upper and lower limit for parametric. Again, it's good to have your weight scale or your mass flow. Parametric requires concentration to be measured as well. Oh, by the way, you want to make sure that your concentration is measured and is not used as a controlling feature by the software. There can be a lot of frustration trying to get the delicate balance between the pressure of EO going in versus the concentration, because you have load effect and as well as headspace and nitrogen pressure over blankets and that sort of thing that can cause difficulty with those two elements getting confused. So use the EO concentration as a unit of measure and not of control if you're doing parametric. Oops, my screen hung up. There we go. Okay. Specification tolerances. When you start setting specification tolerances, a lot of companies like to take into consideration process capability, but you want to be wary of setting limits that the equipment may not be capable of consistently achieving. So if you have someone who knows how to do capability analysis, then this is a really good tool. In this particular example, we established an upper and lower limit for concentration. The lower limit was 300 milligrams per liter and the upper was 400 milligrams per liter. And we said, hey, what is it going to be if we try to have a Six Sigma process? We looked at this, and the CPK, which is the process capability short term, showed that it was within capability 3.32. Anything greater than 1.3 is considered really good. And oh, by the way, when someone did this analysis, they actually said, are we capable of 5 sigma? And then they titled it as 6 sigma. So you want to look carefully at the way the data was analyzed, making sure that if you're looking for a 6 sigma process, you do use 6 sigma analysis and not 5. Otherwise, again, you have a false sense of security as to what your equipment is capable of doing. So for specification tolerances, when you're setting upper and lower control limits, you want to consider the following questions, like what happens if the limit is either not met or is exceeded? And we gave an example of that for time. If your time limit is not met, do you have data on hand to assure that your sterility assurance level was met and your required spore log reduction was achieved? If it's exceeded, do you have data to support the heat history that's delivered to your product, as well as the EO residual levels that may be affected by the product? You also want to consider if there is some remedial action that's required to bring the process back into compliance. So, for example, if you put your product into preconditioning and it's accidentally taken out of preconditioning too early, how do you remedy that? Can you put it back in for another 5 hours, 10 hours? Do you only have to put it back in there for the amount of time it was shorted? Or do you have to start preconditioning from the very start? Again, you want to look at the amount of heat history delivered to your product and what data do you have on file to support putting it back into a full preconditioning process? Or do you have graphs that show if the product is cold, how long does it take it to heat up to the desired temperature before it can be removed? You want to make sure that your preconditioning timestamp was not exaggerated when you set the limit to start with. You want to make sure that you understand the minimum amount of time necessary for preconditioning, and then how much heat history can be delivered to your product before it affects the amount of the quality of the performance of the product by having additional heat added to it. So is there justification for accepting the deviation without remedial action? That's kind of what I was alluding to start with. Do we have data to support the lower and higher values of that limit? Is the limit appropriate or necessary? So for example, if you have a PSI of 0.75231 because you think that it can be that accurate, is that a reasonable or necessary limit? Is it the appropriate limit? If we look at the chamber temperature at the end of processing, let's say you have an all-in-one process and you're flushing the back end of the cycle and you have 16 washes to get rid of the EO. How critical is a plus or minus 5-degree tolerance in that part of the process, given the amount of air and nitrogen and that sort of thing that's going in and out of the chamber? You may consider that to be critical. You may consider it not to be critical. But there are times that we look at a nonconformance and we look at the limits we put upon ourselves, and we say, what were we thinking? Well, it's appropriate to address it and then change it as necessary. In doing all of that, a failure mode analysis is usually a good way to analyze your data. So the set point of the process does not need to be central to the upper and lower control limit. It should take into account the most likely failure mode that could push the parameter beyond its limits. So, for example, if we use exposure time again, and based on all of the data that we did from our sublethals and our MPQ, etc., we need the set point to be 360 minutes. That's going to be the set point for our cycle. Then based on our data, we see that we still have kill and the appropriate spore log reduction in SAL if our full cycle runs at least 340 minutes. So that's 20 minutes shy of the set point. But for the upper limit, we find that we have EO residual data and heat history data to support an extra 2 hours in the exposure phase. So if something were to happen and the cycle were to go over, you have data to support it. You're good to go. So in this particular example, your minimum is 20 minutes less than your set point, but your maximum is 2 hours greater than your set point. So the set point is not central to the upper and lower control limit, and that's okay. So there are times that it may take longer for the equipment to step into the next phase, and you want to be sure to account for that. So setting the set point toward the minimum time acceptable allows for the most time that you have to remedy the problem. So in this example, if we have hit our 360 minute and for some reason the machinery is not stepping into the next phase, the operator may be able to intervene because alarms go off. You know, it says, well, the abater is in use by a different chamber, so we can't step it, or maybe it just thinks it is, and so they can manually force it and they can correct it. So having that upper limit as flexible as possible for certain things, such as time, EO concentration, or pressure, I should say, that's going to give you a process resilience, so that you're not painted it into a very small box that you have to stay into. You want to have as much flexibility as your product and your cycle will allow you to have. So failure mode analysis is a very useful tool to proactively identify and address process deviations. The couple of examples that I've given are good ones to plug into a failure mode analysis. If we exceed this limit, what do we do to remedy it? If we don't meet the limit, what would we do to remedy it? And have your dichotomous chart to say, here's how we're going to do it, here's what we're going to do. Oh, by the way, here's the data that we need to generate in order to support all these. So your failure mode analysis will help to be your identifier and your plan. Develop a plan, make sure that you have process resilience, identify what documentation has been generated, and your failure mode analysis documentation can point to those validations. So it's all in one place. You don't have to go searching through your documentation system looking for keywords. You record it directly in your failure mode analysis document. Here was our concern, here's how it was met, here's the document that generated the data to support the decision that was made or can be made. So a documented review of the potential failure modes and the impact that they could have on the product and sterilization process is valuable. So document, document, document. Leave breadcrumbs for yourself. Don't let any stone go unturned, and document it that it was turned. So most of the disruptions that occur during a sterilization process may be justified as non-critical. For example, if you have too many washes on the backside, is that a bad thing, or can it be justified? It's not critical to the lethality, but it may be critical to other things such as your packaging or product function. So the most critical parameters are around temperatures, relative humidity at the end of conditioning and then stepping into the start of EO injection, the EO pressure increments, the concentration, and again, that's applicable to parametric cycles. Your chamber RH at the end of conditioning is also in association with parametric. Your dwell time, and then your post-evacuation times and depths of vacuum. So we've looked at the measuring systems that are used to control and monitor the processes. We've considered how the selection of the parameter reporting process precision is determined by the instrument calibration. We've reviewed how precision relates to accuracy and how that affects how we report the data that's reflected in the real capability of the monitoring system. And we've looked at how the way we write our specifications can positively affect how we interpret the data and how programming of the cycle can be used to instill a level of precision resilience.
Awesome. Thank you all for attending today's STERIS Tech Talk. We appreciate you taking the time to learn with us, and we hope you found this session beneficial.